other members of the Department of Philosophy and the Faculty of Arts. It's very, very rarely that I get an opportunity to speak as an academic. But in fact, I could say that it's only Charita Era to invite me to give academic talks. I give only political talks. But even this talk is going to be political in a way. And I was just telling Charita, if I were young, say 20 years, I would have spent the next half an hour replying Bhante Samahita. But I'm not going to do that. I'm too old now. And I have to go home after this lecture. So I'll just speak as if Bhante Samahita did not speak. My topic is quantum ontologies and the observer. Now, before I get into quantum ontologies, I should get into classical ontologies, because without classical ontologies, we cannot understand quantum ontology. There are at least 3 classical ontologies that are very interesting, and they are not the same. I am of course just confining myself to classical mechanics and physics in that sense. The first is Newtonian ontology. Then I'll come to special relativistic ontology, then to general relativistic ontology in classical physics. Now, Newtonian ontology assumes that there is a space and time flows in this space, perhaps uniformly. Because there is no other, we don't know whether time flows uniformly. Because if you want to find out whether time flows uniformly, you will have to have a super time. You measure velocities, etc. with respect to time. So if you want to measure the velocity of time or the uniformity or whatever rate of flow of time, then you must have a super time. So we don't know whether time flows uniformly or not, but we'll assume that. It doesn't matter. Now, those things that there is space and there is time flowing in this space are maybe, one can say that they are independent of the observer. But after that, the observer comes into the picture. Not only in quantum ontology, even in classical ontology, observer comes into the picture, because Newton introduced this funny idea of inertial frames of reference. Now, without inertial frames of reference, one cannot define force and acceleration. Newton's laws are valid only in inertial frames of reference. Now, what is an inertial frame of reference? Inertial frame of reference is supposed to be at rest with respect to the distant, far away stars. Now, how are you going to determine these far away stars? What is the distance that you have to measure to get at these far away stars? There is no way of defining it. So that remains ambiguous, and we know that, not that we, the scientists say, that all these stars rotate and they have various other motions. So it cannot be said that there is some frame of reference which is at rest with respect to distant stars. It's true that the distant stars are at rest with respect to us because they are so far away from us. But if you say, develop better telescopes, you may find that they are also moving. I'm not talking of the Big Bang, where everything is supposed to be expanding and going away from the other, but this rotation I'm talking of. So, with the introduction of inertial frames of reference, Newton introduced the observers also. It's only with respect to the observers who are at rest in these, what are known as inertial frames of reference, Newton's laws are valid. In any other frame of reference, with respect to any other observer, Newton's laws are not valid. That is what happens, say, when you go in a merry-go-round, as we are all doing now at the moment in this country. We observe various forces, but that is because we are supposed to be in a rotating frame of reference with respect to the inertial frame of reference. Now, this ontology of Newton, or what I call Newtonian ontology, with the observer, space and time separately. Space and time are separated. They are separated. They exist separately, and the observers also. And in this space and time, there are objects. There are, you might say, radiation and various other things. But space and time are the most fundamental, and they can be probably independent of the observer, but after that, with respect to Newton's laws of motion, the observer comes into the picture. Then I get on to special relativistic ontology, where space and time are no more separated. They are not entangled. They are not entangled, but they are connected in the sense one observer's space may be some other observer's time. There are various transformations. My space would be somebody else's time. Now, space and time are connected. They are interconnected because, that's very easy to find out. Any event happens at some point, at some time. What I measure at space, the distance, may not be the same as somebody else measures as the distance. Or the time, I might say that it happens at 8:05 or 10:05 or 10:20, but somebody else say, no, it happened at some time later. Also, the time interval between two events could depend on the observer, depend on the relative velocities of the two observers. So there is no fixed distance between two events with respect to all the observers. So these are fundamental differences between Newtonian ontology and special relativistic ontology. I'm just going very fast without describing these things, but during the discussion hour, I may be able to explain this in more detail. Then I come to general relativistic ontology. That is again due to Einstein. In general relativistic ontology, space and time are connected, but there are differences. The difference, the most important difference being, whereas in special relativity also, space and time, though connected, space is called space-time, not space and time, space-time, is determined, it exists without objects. Even without objects, space-time can exist. But in general relativistic ontology, space-time does not exist without objects and radiation. Objects and radiation, they are more fundamental. They are more fundamental. And the objects and radiation, or matter and radiation, if you might say. Matter and radiation determine space and time. Not wrong to say space and time. Space-time. Space and time is applicable to Newtonian ontology, but not to special relativistic ontology or general relativistic ontology. So they are combined, but space-time is now determined by matter and radiation. Now, then there are other differences also. In special relativistic ontology, there are these funny people called inertial observers or inertial frames of reference. But in general relativity, there are no inertial frames of reference. That's very important. There are no inertial frames of reference. In special relativity, there are inertial frames of reference, and only in inertial frames of reference, Newtonian laws are applicable. Newtonian laws, of course, modified to a certain extent according to Einstein's relativistic, special relativistic law. There is no gravitation, mind you, in Einstein, in general relativistic ontology. There is gravitation only in special relativistic ontology and Newtonian ontology, but not in general relativistic ontology. I'm sorry, I cannot explain further due to my limitations of time. We have to work in space and time, no, whatever it is. So we are restricted by space-time. But the resultant is really the resultant of the two actions of the two magnets. The two magnets act simultaneously, and the resultant can always be measured. So that whatever the object, whatever the metallic object you place before two magnets will move along the resultant, sort of resultant, due to the two actions of the two magnets. That's called principle of superposition in classical physics. That's a linear experience. You can add them linearly. Linearly means, of course, not arithmetically, but vectorially. Vectorially means taking into consideration the magnitude as well as the direction. That's again linear, whether you take the direction as well or you don't take the direction, it's linear. Now in quantum ontology, the principle of superposition is entirely different. What it says is that in quantum physics there is this equation known as Schrodinger's equation. Relativistic as well as non-relativistic. You don't have to consider relativistic. In fact, you don't have to consider whether it's relativistic or non-relativistic. Just say it's the Schrodinger equation. There are solutions of the Schrodinger equation. Now these solutions come in not just one. There is no unique solution, but there are hundreds, thousands, and sometimes infinite solutions. All these are solutions of the Schrodinger equation that can be applied. And each of these represent a state. Each of these solutions represent a state. Now in quantum ontologies, these states represented by these Schrodinger equation solutions of Schrodinger equation, they are there. Classical objects. We are classical. I am classical because of my age also now. Not only classical, I am I can mental. So we are classical as well as mental. Now in classical ontologies solutions, I can see all of you sitting here. You have a definite position and you have a definite velocity. Your velocity is of course zero with respect to me, but if somebody now moves here, he will have a velocity. He will have velocity, and he will have velocity as well as a position. All these motor vehicles running around, they have a position as well as a momentum. You can measure the momentum. Well, I don't have to use the word momentum, just say the velocity. Velocity is enough. Now what happens if you measure the position of a motor vehicle passing Kalaha junction? You know, let's consider quantum motor vehicle, not the hybrid motor vehicles that we'll have very soon, on the electric vehicles anyway. But let's say one of these quantum vehicles. That quantum vehicle will be passing Kalaha junction. What is the velocity of the quantum motor vehicle? Nobody knows. Nobody knows. Because as far as the quantum motor vehicle is concerned, it has so many velocities, maybe infinite number of velocities, and you don't know the velocity. Whether it has infinite number of velocities or no velocity or one velocity or two velocities, nobody knows. All you know is that it has the position. It has a position. It passes through Kalaha junction. Now, if you want to measure the velocity of the motor vehicle, of course you can set up an experiment and measure the velocity. The moment you measure the velocity, unfortunately the motor vehicle have various positions. So it will be at Kalaha junction, it will be at Taladamanika, or it will be at Peradani, or even it will be even at Colombo, or even Maragama, my home. I don't know. It could be. So there are various positions. So all these positions, all the momentum or not the velocities, are represented by those solutions of the Schrödinger equation I told you. So when a body is in a certain state, say if the position is determined, then in order to determine the momentum or the velocity, you have to perform another experiment. Until then, you don't know the momentum or the velocity. Once you measure the velocity, you don't know the position. It's a funny situation. Right? It's a funny situation, and it's fortunate that we are not quantum. If you were quantum, I would be at this place as well as, that would have been better in a way. I would have been at various other places as well, same time. But we are not quantum, we are classical, and as I said, we are mental also. So we don't know. Now, there are 4 quantum ontologies at present, depending on how you interpret all these Schrödinger solutions. These Nalin Silvas also either shake their hands or kick somebody else or do something which is not what I do, but it's represented by one of the other state solutions of Schrödinger equation. So every time I do something or you do something, these universes go on splitting. It's nothing but splitting. So there are, I don't know how many universes. That's called multiverse. And it's supposed to be scientific and it's supposed to be empirical as well. And people think that science is empirical. That's the second interpretation. The third interpretation is an interpretation that can be given that all these vectors, all these solutions exist. It's an ontological problem exists. But we cannot observe them. We cannot observe, but they exist. Existing without being observed by unfortunate people like us. That's the third ontology. Then there is a fourth ontology that was formulated very recently, about 3 weeks ago, by a person called Prof, with whom I had an argument in the internet, of course. She tells that all these other solutions are potential realities. There's another way of saying, well, we don't know anything about them, right? They are potentia, she said, potentia. So there are at least 4 ontologies present. Now, I think my time is up, even though space, so we had to worry about space-time. Now, just one other problem that I am interested in. Now, there was a man called John Wheeler. I think Reverend also referred to this man. He was one of the most brilliant people ever lived. Though he never won a Nobel Prize for physics, he had so many students who were Nobel Prize winners. I also have so many students who are not with me, right? I mean, politically. So I think after John Wheeler, I have produced so many students who have come to prominence without agreeing with me. So I should also deserve a Nobel Prize one of these days. Now, what he says is very interesting. Now there is an experiment called double slit experiment. I'll just give a one of the most famous experiments in physics. In fact, I suppose the most, not one, but is the most famous experiment. You have a source here, emitting electrons or photons or whatever. Then you have 2 slits. They pass through these slits. And there is a screen. On the screen, you get an interference pattern. Now, wave theory, the old wave theory could explain this, saying that all these photons travel in waves. But then it's applicable to electrons as well. So whether electrons travel in waves is a different story altogether. But whatever it is, these interference patterns are formed. Now what happens if you close one of the slits? Then no interference pattern, because these electrons or photons pass through only one of the slits. You have the coming together of these 2 waves or whatever. I can't explain that in simple words, because there are no words for this phenomena. And they come together and they form interference pattern. But if you close one of them, then there are no interference patterns. It's just like electrons or light passing through one slit, one hole. Now, John Wheeler, some time ago, maybe 20 years ago, he said, what happens if you close one of these slits after the electrons or the photons pass through the slits? That's a funny question. What happens if you close one of the slits after the electrons pass the slits? Then again the same phenomenon. If you close one of the slits after, right? Underline after the electrons pass through the slits, even then you will get no interference pattern. But we might think that the electrons or the photons have passed through both slits, because we are closing one of the slits after it has passed. Now, how do you explain this phenomenon? Well, my explanation, which I am telling for the first time to the world, and you happen to be the first time to hear this. Whether you are fortunate or unlucky, I don't know, to hear this for the first time. That the photon or the electron pass through two slits after with respect to us. After with respect to us, the time is measured with respect to us. What happens, what is the time with respect to the photons that pass through the two slits? I'll say time is not defined. It can be everywhere and it can be in all time. Only the energy and the velocity or the momentum of the photons or the electrons are determined. When the energy or the velocities are determined, the position and the time are not determined. This is from Ontology, uncertainty principle. So if these particles have a definite energy, definite velocity, then they can't have definite time or definite position. They are all over. They are all over and they are not all over in space, all over in time as well. So whether we close the slits after they have passed the slits with respect to us, with respect to the photons, nothing has happened. Nothing has happened and one of the slit is closed. Not before or after, but one of the slits is closed. So you can't have interference pattern. So
is it only one state that it's closed? Is it only one state that it's blocked? Only one state?
Yes, only one. No, only one state, right?
State. Go ahead.
Only one state, yes. Only one state. And the slit is closed. And when the slit is closed, what I am trying to say is that it's real. We close the slit supposed to be after the electron or the photon has passed through the slit. But as far as the electron or the photon is concerned, it is not after or before. Not after or before, it's just in time. There is no time. Time is not defined. So that's another kind of ontology that I might say, a fifth ontology, which might explain John Wheeler's experiment or delayed action, delayed measurement. So with that, I close my presentation, and we may be able to have a discussion. And if you haven't understood anything, then there won't be any questions. If I understood something, then hopefully there will be some questions, and I will try to answer you. Thank you.